Hello everyone, welcome you for the link budget analysis for 5G network under 5G technology 2. I have referred the content for preparing this material as 5gtools.com. They have created very good platform for calculating the link budget analysis, where link budget is a mathematical calculation used to determine whether a radio signal transmitted from 5G base station 5G G node B can be successfully received by the user equipment with a sufficient power. It accounts for all gains and losses encountered by the signal during the transmission. The purpose of calculating the link budget is to establish the cell coverage, determine maximum communication distance, verify receiver sensitivity, assist in network planning, and to compare the uplink downlink performance. So the received signal strength depends upon the transmitter power, antenna gain, propagation losses, feeder losses, fading margin, and receiver sensitivity. So this module, the 5G tools, 5G calculator, actually, it finds the balance between all transmitter gains and all propagation system losses. Whether received power, how can we calculate the received power means in terms of the transmit power by adding the transmit power and the gains by subtracting the losses, various losses. If we look at this figure is taken from 5G tools for representing the what are all the entities are placed between the transmitter and the receiver. Okay, for that purpose I have taken this is the base station represent the transmitter, and the user terminal is receiver. So the height of respective terminal is represented by base station HBS and HUT, and the transmitter here, if we consider this is the transmitter, so the transmitter power G node B transmitter power, and the antenna connected with the transmitter, so G node B antenna gain represented here. In the same way for the receiver, so for the receiver user terminal antenna gain, and the reception sensitivity might be user equipment reception sensitivity 1 and 2. Based on the threshold value, we can identify whether the successful connectivity is there or not between that. And here, other than that transmitting power, antenna gain, we have a few more parameters involved in that. That is nothing but the losses. So the cable losses, the transmitter, for making this connections, a lot of cables will be inserted. So that losses, cable losses, should be subtracted from the transmitted power, and the path loss between the transmitter and receiver. What the propagation model depends upon the propagation model, the path loss is estimated, and that should be subtracted from the cumulative value. Then the penetration losses, foliage loss, slow fading margin, all this red mark represent downgrading. That means a subtracting component, the rain IC margin, and then body loss or cable loss of the user terminal. Okay, this everything is a subtractive component of this. So the general equation for calculating the received power, PR equal to PT plus GT, where PT transmitter power, transmitting gain, and receiver gain, all this additive component, and from this we can subtract the losses, path loss, and then medium losses and the free space losses, so that everything we can subtract. So for the 5G network, this equation is modified into link budget, signal level at the receiver. Okay, link budget. So by including all parameters. So first, the additive component, let us look at transmitting power. Okay, so the transmitting power, antenna gain, transmitting antenna gain, then received antenna gain. here plus received antenna gain parameters. Okay, then the subtractive component, all the losses supporting to this. So the cable loss, transmitting cable loss, subtract the receiver cable loss, then the propagation path loss to be subtracted, penetration losses, foliage losses, body loss or cable loss, interference margin losses, rain ice margin losses, slow fading losses, penetration losses at the indoor, and attenuation losses at indoor. That everything to be subtracted from the component of transmitted power and the transmitting receiving gain. Okay, so this is what the formula supporting the 5G link budget calculating. As I have mentioned, it is very important to analyze whether the, suppose if you want to establish the better coverage, then based on this calculation we can decide whether we have to go for micro macro structures or cell based structure or cell free structures, so we can go for. Okay, so based on the formula we can discuss one example or the scenario. This scenario created for the link budget and reliability analysis for the 5G URLLC for the industrial cell. Okay, controlling in an industrial cell. So first we will see the problem statement. A 5G G-node be operating at the carrier frequency 3.5 GHz serving services URLLC. This device is located into the factory floor. If you are required to perform the link budget calculation and you need to evaluate the physical link and SNR target adequate margin for the URLLC reliability. So what are all the data are given mean the carrier frequency given and two different scenarios we have to discuss with the distance d equal to 50 meter, d equal to 200 meter and the transmitted power 23 dBm, transmitting gain 8 dBi and received gain 0 dBi, cable losses associated with transmitter and receiver is 1 dB, noise figure 7 dB and SNR required for robust modulation is 5 dB, then shadow margin. Usually for the URLLC cases, the shadow margin factor most considerable. So that factor equal to 8 dB. Implementation margin is 3 dB given. What the task we need to perform here means for the bandwidth 180 kilohertz with the distance d equal to 50 meter, d equal to 200 meter. What is the effective isotropic radiated power, free space path loss, noise floor, receiver sensitivity, received power, and the final effective margin. This everything we have to calculate. And next, the all this parameter calculation for the scenario B also, that is with distance 200 meter we have to calculate. Then the third task, you have to compare scenario A, B with d equal to 50 meter, 200 meter. What will be your noise floor, receiver sensitivity and the received margin. Okay, that's the thing we need to discuss. Now one more case included with the bandwidth 1 megahertz. That means distance 200 meter, bandwidth 1 megahertz, bandwidth 10 megahertz. Then how the URLLC performances varies, that also we have to comment on this. So we have already discussed the formula. So directly how to solve the problem. Sorry, this formulas now only we are going to discuss. So effective isotropic radiated power calculated by PT plus GT minus your loss, transmitting loss, and the free space path loss can be calculated by 20 log 4 pi d by lambda, where d two different d given, d equal to 50 meter, 200 meter, and lambda value we can by this formula you can calculate C by F. C equal to 3 into 10 to the power 8 and F 3.5 gigahertz is given. By substituting this lambda value you will get. Then for the two distance you can calculate the free space path loss. Then noise floor, N0 equal to minus 174 dBm per hertz plus 10 bandwidth. Bandwidth for the scenario A 180 megahertz and for the scenario B with 1 megahertz and 10 megahertz we have to analyze. then the receiver sensitivity, N0, NF, SNR required, and the margin, implementation margin. By adding all this component, you can calculate the receiver sensitivity, received power, EIRP plus GR minus path loss minus received cable loss. Receiver cable loss, you can calculate received power, and finally link margin, whether the link is pass or fail. To analyze that, received power minus P sensitivity. So most probably the positive margin should be there for link margin should be there for positive, so that it will reach the maximum target of signal power. Okay. So now by substituting all the values, f equal to 3.5 GHz, C 3 into 10 to the power 8, we can get the lambda value equal to 0.0857 meter. Then E effective isotropic radiated power in the formula, we got 30 dBm, and free space path loss for the 50 meter, it is 77.30. Noise floor component with 50 meter, 180 kilohertz, it is minus 121.45 dBm. And the receiver sensitivity, the formula, receiver sensitivity additive of all the components, so minus 106.45, received power minus 48.30, link margin 58.14 dB, and after subtracting the shadow margin, the effective margin value equal to 50.14 dB we got. Next, the analysis we have to do, that is with the distance D 50 meter, 200 meter, with the bandwidth 180 kilohertz, what will be the power sensitivity, received power sensitivity, and the link margin value. Okay, and then noise power irrespective of the distance, so it has remained constant. And for the scenario B, 200 meter, okay, with 200 meter, two different bandwidth, 1 megahertz and 10 megahertz, receiver sensitivity, and the link margin value. Link margin decreases as the increase of the bandwidth, link margin decreases. Okay, after shadowing it is decreases. So here what kind of interpretation we can get? Larger allocated bandwidth, right? Larger allocated bandwidth raises the noise floor and reduces the noise margin. This is what the observation we have received from the previous one. And the interpretation for the URLLC consideration need very high reliability. So link margin alone doesn't guarantee the packet error. And then what is the next interpretation? Large power margin gives headroom to apply the fading margin, tolerate interferences, or reduces the transmitter power to save energy while meeting the reliability. So if the margin value is small or negative value, what kind of remedies we can take? We can increase the antenna gain, or MIMO concept, multiple input, multiple output, beam forming concept we can introduce, or the distance between the transmitter receiver we can reduce, allocate more power. Allocating the more power, increasing the complexity of the systems. So one of the remedial action is allocating the more power, but it is not preferably, and reduce the bandwidth used for the critical packet, then repetition or retransmission of information upon the request, or use the lower order modulation technique and stronger coding. Stronger coding technique, source coding or channel coding technique we can use to improve the service. So for indoor factory deployment, remember the account of blockage and multipath, non-line of sight, free space path loss is the baseline. We have to look at all these components for the analysis. Okay, so these are all the interpretation required for the URLLC consideration, and this is the second task with urban macro cell scenario. The same way, the formula, standard formula will be there for calculating the free space path loss, and you can calculate it, the calculation given, and based on that we can take the interpretation for the URLLC. So these two problems are very much important. You can explore it, and the website what I have referred 5gtool.com, that also very nice, informative and user friendly. You can try that. Okay, so thank you very much for your listening.